In this video, we'll figure out how to solve the range minimum query problem really fast. It appears in many other problems like finding the lowest common ancestor in a tree or finding the longest prefix in a string. In fact, the data structure we will come up with can be modified to solve many problems not related to finding the min. The RMQ problem is very straightforward. There's an array of size n and we get many queries on this array. Each query is asking us to find the minimum value between the lth and the rth element. For instance, m3, 5 is equal to the min of 8, 1 and 5, which is 1. m04 is the min of 7, 4, 5, 8, 1, which is also 1. The straightforward solution to this problem is to answer every query by iterating from the lth element to the rth element. Although this could be really slow since it can take up to O of n time per query to answer. Let's see how we can use preprocessing to make our queries faster. Preprocessing is when we analyze our array at the start of the program and then use it to answer queries in the future. During preprocessing, we compute the answers to all possible queries and store it in a table. In the first row of the table, we'll store the answers to queries which start at the 0th index as shown. To compute this, we start at the 0th index and maintain the minimum as we iterate until the end of the array, while storing the current minimum at every step. We would do this for every starting index. Once we have this table, we can answer any query in O1 time by just looking at the table. However, we have shifted all the hard work to preprocessing, and as a result, memory and time required for preprocessing is order n squared. This quickly becomes infeasible for larger arrays. Using the power of divide and conquer, we will discover how we can keep constant time queries while having much faster preprocessing and a smaller memory footprint. Let's dive in. Let's look at the query from 3 to 14. This is a pretty long range covering almost the entire array. We can break this range from the middle into two smaller ranges, from 3 to 7 and 8 to 14. If we find the answer to both the pieces individually, then we can find the answer for the query by taking the min of both of them. In fact, this will work for any query given that it crosses the center point. But what's the point of breaking it into two ranges? Well, if we store the min of all ranges starting from or ending at the center point, then we can easily find the answer to the subqueries. We can do this in the preprocessing step and store it in an array called A1. Let's see it for the left half. To start, the 7th index value will be identical to the input array. For the one to its left, we will store the min of the 6th and the 7th element. At the 5th index, we'll store the min of all elements till the dashed line, which is 8, 5 and 7. Keep doing this for all elements until we reach the start of the array. Now repeat the same for the right half, but now we'll move in the other direction. Start by letting the 8th index be the same value as the input. The 9th element will be the min of the 8th and the 9th element, and so on. After this, our A1 array is finished. The ith element in this array contains the min from index I to the dashed line. Going back to the M314 query, but this time we'll use A1 to calculate the answer. Notice how we've already saved the answer to the left range when we were computing the left half of A1, and the same for the right half. Well, we can combine both the subqueries by taking the min, and this allows us to calculate the query answer in constant time. More generally, if our query crosses the center point, then we can use A1 to answer with this formula in constant time. That's great. We can now solve queries in constant time. But this method only works if our queries crosses the center point. If L and R are both in the first half of the array, we can't use A1 anymore, since that contains the ranges originating from the center point. This is where divide and conquer will help us out. We know that a query either completely lies in the first half or it completely lies in the second half if it doesn't cross the center point. Let's draw a solid yellow line to indicate the two partitions created. Now we will repeat the same approach, but this time it will be through the midpoints of each partition. A2 will hold the values from the dashed line to the ith index within its own partition. Let's see it happen for the left partition. Now let's see this for the right partition as well. Using A2, we'll answer the query from 1 to 6. The range doesn't cross the center point, so we can't use A1, but we can use A2. We break it through the midpoint of the partition, which is the first dashed line. A2 already stores the answers of both the ranges, and this allows us to calculate the answer in constant time. Another example, but this time the query lies completely in the second partition. That's great, we can now use A1 to solve any query which goes through the midpoint of the whole array, and we can use A2 to solve any query which crosses the midpoints in the partitions, which are the yellow dashed lines. But we aren't done yet. What if the query doesn't cross any of the lines? This is where we'll use divide and conquer to split each partition again into 2 pieces, giving us a total of 4 pieces. Then we repeat this approach and store it in A3. Right now each partition has 4 elements. If we split again, we'll get a partition size of 2. At that point, the A4 value will be the same as the input array, so there is no point in dividing further. Let's just stop here and bring A1, A2, A3 into the same screen to figure out how we can use these to answer any query. The arrows make it easier to visualize what value is stored in each of the A arrays. The last piece of the puzzle is to find which array will help us compute the final answer. The straightforward approach is to start from A1 and check if it's valid. If it isn't, then we can move on to A2 and so on. But this would be too slow since there are a logarithmic number of levels. We need to figure out which of these to use in O1 time so that our final query time can also be constant. The trick is to look at the indexes from 0 to 15 in binary. Intuitively, the number of partitions we have is always a power of 2. Whenever we split, it doubles the number of partitions and each partition is now half the size. The binary values of the indexes follow along neatly with this pattern. The first thing we notice is that all red boxes start with a 0 and all blue boxes start with a 1. This implies that to use A1, L has to start with a 0 and R has to start with a 1. Looking at the left partition of level 2, we see that the first bit is the same in all of them. The second bit is 0 for the left half and 1 for the right half. This implies that for A2 to be valid, the first bit of L and R must be the same, and the second bit must be different. Looking at a partition of level 3, we observe a similar pattern. The first 2 bits are the same, and the third bits differ between the left and the right half. Let's take an example of 5 and 11. 5 and 11 differ in the leftmost bit, so we know that we must use A1. We can verify that this is correct since 5 and 11 cross the middle point of the array. For 9 and 13, the first bit is the same, so we can't use A1. The second bit differs, and hence we can use A2. For 5 and 7, the first 2 bits are the same, so we can't use A1 or A2. The third bit differs. This means that we must use A3. If we take the bitwise XOR of 5 and 7, something magical happens. The bitwise XOR is an operation on the bits of the same columns. If the bits are the same, then the output bit is a 0. If the bits differ, then the output bit is a 1. So taking the XOR of 5 and 7 makes the first 2 bits a 0 and makes the third bit a 1. The position of the leftmost 1 bit of the resulting XOR will tell us which level to use. We can compute this in constant time since XOR and leftmost 1 bit are both constant time operations. In C++, you can use special built-in functions to get the leftmost 1 bit. Otherwise, you could pre-process this for every XOR output possible and store it in an array. Once we find the correct level, we can simply use that array to compute the final answer. The trick with XOR only works if n is a power of 2. If it's not, then the bits won't cleanly line up with the partitions. Fortunately, if n is not a power of 2, then we can add null elements to the end until it becomes a power of 2. In the worst case, our array size doubles, but this won't change the time complexity since it is a constant factor. During preprocessing, in every iteration of the divide and conquer, we split our partitions into 2 until the partition size becomes 4. That means there are log n minus 1 levels. Every level stores n elements. That gives our preprocessing memory to be O of n log n, which is much better than the quadratic memory we were using in the previous solution. Computing this also takes n log n time, since every value in the array can be computed by looking at the input array and its previous element. The query time is O of 1, since we need to find the level and then take the min of 2 elements. Each operation in this is constant time, so overall we have a constant time query. Some concluding notes to finish out the video. Throughout the video, we didn't use any special property of min. The only property we assumed is that we can compute the min in any order. This data structure would work equally well with any other associative operators, such as addition, matrix multiplication, and convolution, which shows just how powerful it is. In terms of performance, nlogn is not the best. We can do even better if we make blocks of size k and recursively apply this data structure to the subblocks. The resulting data structure would have nlog star in preprocessing time. It's a bit more complex to explain, so I'm going to leave this topic for a future video. Lastly, this data structure is not very common, and I only discovered it while solving a problem. I've seen this been casually referred to as the disjoint sparse table. If you guys have any better names for it, please leave a comment. Thank you for sticking to the end, and I hope you learned a bit more about data structures today.